which I think is a beautiful quote. So that's where I am starting with, just so that you see. Now let's go to the next slide. Yes, let's go to the next slide. Yes, let's go to the next slide. Now here, there's the plan of the talk given. I don't know what else to do with it, because the way I would do it is to show it first and then show it whenever to explain. But let's see what can be done. Somebody, Manzoor Sumro, is finding the voice low. I don't think anybody else has said that. So here there are the various topics, and no point in my reading them out. You'll see them as we go, and a total of 59 slides here, because the first 3 slides are already what we have seen. Let's proceed on. Let's proceed on. When I returned from England after my PhD, I attended conferences in which mathematics would be extolled with inane arguments and analogies, claiming, for example, that mathematics is used everywhere. Please go on. And then they justify the claim by saying, when you go to a shop, you have to use mathematics. Please go on. An obviously specious argument, as the shopkeeper adds the columns of number better than the mathematician does. So that is clearly not a good example. Another was, mathematics is the mother of the sciences. Please go slow, because I want to stress on each. So mathematics is the mother of the sciences, as if she has her children, the sciences, sitting at her feet, playing with their blocks and cars and guns. Yet another is that mathematics is the queen of the sciences. Proceed, please. Yes, please proceed, please. As if she is holding her scepter and her courtiers, the sciences, are standing around waiting for her favors. Please proceed. Next slide. These flights into inanity do no credit to mathematics. To the contrary, they do it great disservice. To understand why I'm so harsh in my criticism of these platitudes, you need to follow what mathematics is, and not only what it isn't. Before going on to that, I need to debunk other myths. So let me first debunk the other myths. I was invited to give a talk on the importance of math in everyday life, or the beauty of math found in things around us. Those were the titles given. When they say everyday life or around us, have you ever wondered whose life or around whom? Is it the life of a NASA scientist, a student in PIAS, a Pakistani farmer, or hunter-gatherer in some jungle? Who? Please proceed on. Their everyday lives could hardly be more different. Next slide. People often ask us working in basic science, what good is it? Please, next. My answer is with the questions. What good is money? What good is medicine? Engineering? Entertainment? What good is anything? Now, one alleviates poverty and so makes life easier. The next, suffering and hence makes life easier. The next, engineering, that is, to make tools to make life easier. The last provides enjoyment. All the others are equally good for animals. They'll be as useful for animals as for humans. But for humans, entertainment provides joy. That joy is something very human. And the most lasting enjoyment comes from understanding. Please go on. That's basic science. Now, for that matter, what good is education? The usual answer is to enhance earning capacity. And it is a myth, and a pernicious one at that. You see? Now, Nawaz Sharif and Asif Zardari, or for that matter, Al Capone in his time, made fortunes with little education, while Marie Curie and I never did, despite much more education. Let's proceed. Education broadens the mind. It doesn't broaden the wallet, it broadens the mind. Now, mathematics itself appears to be a whole class of topics and not a single indivisible entity. That is where, actually, let me get hold of this thing and take it away here and go that way. Yes. Yes. So does mathematics actually exist, or is it just a collection of mathematical subjects? What precisely is mathematics? Please, next. And that precisely there is the answer. Proceed. Having talked of what mathematics in education, for that matter, are not, we need to go on to what it is. Let's proceed. Mathematics is a class of languages built, please don't go too fast. That loses the whole point of how I've prepared the slides. Mathematics is a class of languages built for precision in poetry or with puns. The great thing is the many meanings associated with very few words. And that appeals to the emotions. In mathematics, a word means one and only one thing, thereby excluding emotions. It is precise. Proceed. Now, next. Whenever and wherever precision is required, mathematics will be applied. Even lawyers need it, though they may not be aware that they do. They need it for clear and precise arguments. Obviously, scientists and engineers and economists need to use it to make their analyses precise. Dr. Manzoor Sumro says the topic is important and he's not being able to hear. So share this subsequently, okay. So what I'm saying is, mathematics is a toolbox of most adaptable tools. Proceed, please. Yes. But then, how can there be beauty, when I'm talking about beauty, without mathematics? I just said it eliminates emotions, and it's just then by itself. How can that be? Well, let's take an example of mathematics that is used, as they say, more or less everywhere. Pythagoras' theorem. You may remember the geometric proof by constructing a lot of confusing squares over each side of the triangle and then trying to show that the areas come out equal. Or the algebraic proof by looking at the ratios and arguing with the ratios. But here is a really elegant geometrical proof found in a Muslim manuscript of the 9th century. 9th century, that far back. It gives the next slide and then simply says, look. Please, just the next slide started. Yeah, now wait. You see, this is a plus b whole square. Each side is a plus b, and that's the square is a plus b. The second one also is a plus b whole square. Now go, just click further. Click further. A plus b whole square in the first figure is equal to c square plus 4 times these triangles. All are obviously congruent, and the area of each is half AB, so it's 4 times half AB. So C square plus 4 times half AB. And A plus B whole square, according to this other figure, is A square plus B square plus these two rectangles, which is therefore 2AB. Now that 4 times half AB and 2AB are obviously the same, so A square plus B square equal to C square. And that is just saying, look. Please proceed. Next slide. Now I ask you, just look, is that beautiful or what? Just look at it. Proceed on. Is there any ambiguity? Is there lack of precision? No. You see? But is it not beautiful? Proceed. It is useful, but who cares? It leaves one with a feeling of awe and elation, not because it is confusing and mystifying, but because it is so crystal clear. Everything is laid out before you. Any child can see it. In fact, my 13-year-old grandson, no, that 12-year-old grandson did this for a science project and explained it. And a lady who came to ask about it said, now for the first time I've understood Pythagoras' theorem. It is that simple and that beautiful. It is, I see, that's what you said. Now, the problem generally is that mathematics requires a lot of background to be able to appreciate its beauty. Please proceed. However, there's a simple one to see. One can find infinitely many integer solutions for the Pythagorean theorem. 3 square plus 4 square equal to 5 square, or 5 square plus 12 square equal to 13 square, and so on and so on. Please proceed. Now, how about for A cube plus B cube equal to C cube? You see, there are none. How come? There was, how come there are none? Maybe it would work for some higher power, not 3, 4, 5, 6, something. Or for even powers, maybe 4, 6, 8. Maybe for prime powers, maybe anything. Now, the French jurist Pierre de Fermat, 1607 to 1665, note the years, was an amateur mathematician and put forward various mathematical riddles as challenges to professional mathematicians, for each of which he had a proof that he would reveal if everybody gave up. Please proceed. And I imagine him gloating afterwards. Next. He wrote all the proofs in the margins of his law books. He put the problem of the proof of the non-existence of integer solutions of a to the n plus b to the n equal to c to the n to be solved by the mathematicians. And in his margin, he wrote that he had a proof, but it was too long for that margin. So the implication is that it would have taken a page or two and not fitted into the margin where he normally wrote his proofs. Please proceed. Now, all the other problems that he had presented got solved, or the proofs were then seen. People said, we can't do it, you tell us, and he went ahead and told. The last one left, Fermat's last theorem. Please proceed. Now, many tried to answer, but none succeeded. Someone suggested to the great mathematician of the day, Carl Friedrich Gauss, to tackle it. He said that he would not waste time on it. As per Aesop's fable, please proceed. The fox said, the grapes are sour, not worth doing. Well, they're not worthy of the great Gauss to come up with that. But finally, in 1993, note 16, whatever, 1665, he was even dead. 1993, the English mathematician Andrew Wiles, were using work of mathematicians all over the globe, finally proved Fermat's last theorem in a total of over 300 pages. And yet there was a lacuna pointed out by a referee, and he worked on filling it with the helpful criticism of the referee and completed it in 1995. Of course, with many more pages added in. Yes. Now, people recalling Fermat's claim still look for a simple proof. Well, maybe one of you will find a simple proof. Nobody has so far. The next one. This is even easier to state. We all know that prime numbers, what they are, numbers with no factors to them. Every number can be uniquely written as a product of prime numbers, called the prime number theorem. Now, Goldbach conjectured that every even number can be written, not uniquely, as the sum of two prime numbers. And this is being checked to enormous numbers, but there is no proof for it. Please proceed. When I was 3, this is now coming to counting infinity. When I was 3, my father used to sit me on his knee, facing him, and he would rock and count the beads with me in his lap without any actual beads around. We just would go rocking and say the number. When we got to 10 with great excitement, we would say bundle. Then when we got to 10 bundles, it was a bundler. Soon I was counting them in my head and realized that with new names like bundle and bundler, there was no limit to how far I could go on counting. That was exciting. You can go on and on and on. But the question arises, is there no end? How can we know that? Just go on counting numbers? But you will stop sometime and then there will be no more counting. You see, you cannot count infinity, can you? Well, how many prime numbers are there? Please proceed. Again, there are infinitely many. Euler's argument is to multiply the consecutive sequence of primes up to anywhere and add 1. Then the new number cannot be divided by any of those primes, and hence it is a new, much larger prime. Thus 2, 3, 5 being successive primes 2 times 3 times 5 plus 1 equal to 31 is prime. Please proceed. How's that for a beautiful argument? Lovely. Actually, there's a slight complication. Please proceed. More rigorously, let P be any number P1 to N and Q equal to this capital P plus 1. Now, either Q is prime, in which case we have the larger prime, or it is divisible by some P in the list. Then P divides P plus 1, and it divides P, which implies that it divides the difference between the two. Since it can't divide 1, Q must be prime. That is the full rigorous argument. Now, this original argument was actually even Euclid had. But at that time, nobody had algebra. That was provided by Al-Khwarizmi. And so it's only after that that Euler could get where he did. So then there must be fewer primes than all numbers, right? After all, primes are few and far between among all the counting numbers. However, to every counting number n, there will be a prime number capital N, which is the product of all successive primes up to the nth, plus 1, where with that caveat included, then you get it. Hence, there are just as many. You have just as many. So we have counted infinity. The number of primes is the same as the number of counting numbers, so it's counted. The natural counting numbers are denoted by this n. Now, the number of elements in a set A is denoted by this modulus A, called the cardinal number, which can be infinite. If we denote the set of prime numbers by P, we prove that the modulus of P equal to the modulus of N, it's the same. Now, fractions are called rational numbers from ratios, denoted by Q. Please proceed. Surely Q is greater than N, isn't it? After all, Q consists of the following. Now, this is just those that are less than 1, and look, we've got an infinity, and then another infinity, and then another infinity, an infinity of rows, each of which has infinitely many. Looks enormous. Please go on, press again. Yes. This is the fractions less than 1, yes. Press again. You see, this is contained in n cross n in some sense. Now, with this n cross n, here we go. Please press again. Yes, please press again. You see, I start over here with this in this n cross n, 1, 1, then 1, 2, and then I go down to 2, 1. So this is in the first diagonal, there's 1 element. In the second, there are 2. In the third, 4, 5, 6, so there are 3. In the fourth, 7, 8, 9, 10, so there are 4. And it will proceed that way. To every pair, there will be a counting number. To every counting number, there will be a pair. And I will be able to determine it by just first eliminating the number of diagonal lines, and then in the last one, counting how far you have gone. So that is where we get to. Please proceed. Yes. For every PQ, as I said, we can find an N, and we'll see how with the row, there's 1 element, and the second row 2, and so on. So we can count n cross n. Hence, we can count Q. Sets that can be counted are called with surprise, yes, countable. Well, let's proceed. Then are there any uncountable sets? Haven't we just said infinity is infinity is infinity? Well, there are irrational numbers like square root 2. Please proceed. Yes. When the Pythagorean society discovered irrational numbers, the square root 2 is not a real, is not an integer, is not a fraction as a rational number. So they made every member of the society swear an oath of secrecy, never to divulge this mathematical truth, as otherwise people would lose faith in mathematics and go crazy. So we have to keep this secret. Now, the set of all numbers on a line is called the real numbers, R. For example, square root 2 can be identified on the line by using a compass, a protractor, and ruler. Mark out a unit segment on the line and a unit perpendicular to it. Now use the compass to bring the hypotenuse, the square root 2, down into the line. So square root 2 lies in that line R. So we have the real line contains all of these others. Yes, surely, Manzoor Sahib, it is a whole lot more, and towards the end we will go there. But if I try to give everything in one go, neither can I manage to convey it, nor can you manage to understand it. It takes time. रियाजी रियाज से चलती, उसमें कोई जल्दी नहीं कर सकता. So let's go to the next thing. No, back please. I was just going to continue with that. Back, please. Back, please. Back, please. I want to go back one slide. You've gone forward. I need to, yeah, this one. Here the question can be asked, A, B, and PQ, do they have the same number of points? Oh, no. One is shorter than the other, but do they have the same number of points? Both have infinitely many. Well, as there's a one-to-one correspondence between the two line segments, there are as many points in both. So that is the argument that the number of points in any line segment is the same infinity, one-to-one correspondence. It amounts to the same thing. Now let's go to the next. Yes, please. So getting back to our question, can we count the set of real numbers or not? Now I give you Cantor's argument. Suppose we can, then certainly we can count the points in the interval 0 to 1. Open interval 1, we don't include 1. Let us denote them by decimal fractions and let Aij be digits, that is numbers between 0 and 9. Then there must be some one-to-one correspondence between the points of 0, 1 and the element of n. Please go to the next slide. Here is that one-to-one correspondence that we assume. 1 is 0.A11, A12, A13, up to A1N and on. 2 is, this is whatever that number might be, however you could do it. Suppose there is the one-to-one correspondence, then the list here is going to be given that way. Please proceed. So define Bij to be digits such that Bij is not equal to Aij. And now construct this diagonal element, node point B11, B22, B33, Bnn. This number does not correspond to 1 because the first digit is different. B11 is not A11. Not to 2 because the second is different, B22. Not to 3 because the third is different. Not to n because the nth is different, and so on. Therefore, this number does not lie in that supposed list. So that list is incomplete. Reductio ad absurdum. Please proceed. Please proceed. Hence, there are more numbers in 0, 1 than in n, and so many more numbers in R than in n. So R is uncountable. It cannot be counted. Yes, the next. Please, the next line, yes. Just as an aside, Cantor died crazy. Denote by aleph null the cardinal number or number of elements in the set of n, and by C, aleph null is of n, and by C for R. Okay, let's proceed. Clearly, C is greater than aleph null. That is what Cantor proved. As there are more points in R than numbers in n, continue, the question arises whether there's any cardinal number between aleph null and C. Well, no one could answer this question. Very strange. No one can answer that question. All are looking at it and trying. Well, they won't be able to answer, so they did what mathematicians generally do. They put forward a conjecture. The two are equal. So that's the answer. And proceed on with that. That seems a reasonable hypothesis. In this spirit, the continuum hypothesis was proposed that there's no transfinite number between aleph null and C. Please proceed. Please proceed. One needed a proof of this hypothesis. Are there any other transfinite numbers? Well, we can construct the power set being the set of all subsets of the given set of any set. Using the theory of ordered sets, it can be shown that there cannot exist a one-to-one correspondence between the power set P of A and the original set A. P of A, that's 2 to the A, is greater than A, the modulus. That's the, therefore, P to the N equal to 2 to the N equal to aleph null is greater than, aleph 1 is greater than aleph null. And P of P to the N, the power set of this power set, is 2 to the P of N. That is by definition aleph 2, and it is greater than aleph 1. Please proceed. So the continuum hypothesis is C equal to aleph 1. Let's proceed. The problem was still that no one could prove it. Please proceed. At this stage comes Gödel. In 1931, Kurt Gödel proved the most terrible, negative, disastrous theorem. If the Pythagorean theory society had been around, they'd have prescribed it immediately, shut it away. It probably have killed Gödel in any case. The great thing, according to some, the worst thing about mathematics is that to every question there's a definite answer. Please proceed. Right? Wrong. Terribly, horribly, disastrously, incredibly wrong. Go on. Gödel's theorem. For any finite set of axioms stated in an arithmetical language, there will always be a statement that cannot be derived from that set, finite set. Mathematics is necessarily incomplete. The continuum hypothesis can be chosen to be true or false. Both are okay. Good grief. Proceed on. Kurt Gödel died crazy. Let's proceed. West followed. There was during in the Second World War, and he proved that every mathematical problem could be solved in steps by a computer. Even for an infinite number of steps, it would be countable. You see? Thus, the set of all computable numbers would be countable, and so there must be real numbers that cannot be stated exactly. Alan Turing died crazy. Let's proceed. Some questions. Are all numbers other than the natural numbers unnatural? Are all numbers that are not rational numbers irrational or crazy? Are those numbers that are not real, unreal, or complicated? This one is not so weird as you might think. A VC of Qadir University opposed my going to a school on complex analysis because, she said, Pakistan, the problem with you people is Pakistan needs real analysis, not complex analysis. Here is an equation that has been touted as the most beautiful equation in mathematics. E to the iota pi equal to -1. What's beautiful about it? Well, transcendental number to the power of imaginary times a geometrical number is equal to a negative integer. Though people tried to explain phenomena, those are the elegant applications of mathematics. Though people tried to explain phenomena by linear differential equations, most required nonlinear differential equations. These nodes, nonlinear ordinary differential equations, can have fewer constants than the order of the ordinary differential equation. So Manzoor Sahib, here we are going beyond those numbers. Sophus Lee managed to set up criteria to be able to determine when a scalar second order node can be converted to a linear one. You see, the requirement was that it be at most cubically semilinear and the coefficient functions satisfy the 4 first order conditions involving 2 arbitrary functions. Those are not then to be solved. They are 2 arbitrary functions, and you just have to check that they satisfy the requirement. Proceed on. Yes, proceed on. One then has the problem of finding out how to transform the nonlinear differential equation and then actually solve it. Okay, proceed on. The generalization of the flat space straight line in a curved space is called a geodesic. Its ODE is a second order node that is quadratically semilinear. On projection down one dimension, the system becomes cubically semilinear. So it's non-linear, but the second derivative of the term is by itself, and then the other function is a polynomial, which is a cubic polynomial in the first derivative, with the dependent and independent variables coming in any arbitrary combination. Using this for projecting down from 2 to 1 dimensions, a cubically semilinear, sorry, I'll just take this out from here. Semilinear ODE with the Christoffel symbols giving the coefficients, they satisfy these Tressé constraints. Let's proceed. The metric tensor can be constructed using the Christoffel symbols as the coefficients of the nonlinear differential equation. And in the coordinates in which it is linear, the metric tensor is Cartesian, and the transformation to it can be obtained. That had been done earlier. Hence, the linearizable node can be fed into the computer. Note that you could just put it in and you will get the general solution. If it satisfies the conditions, you'll get the general solution. This was extended to higher dimensions. Let's proceed on. Relativity unified, there's another application. Relativity unified space and time to a space-time, but it is often useful to split it back. This process is called space-like foliation of the space-time. Can one foliate a given space-time into a sequence of flat 3D spaces? This entails solving 6 nonlinear partial differential equations for 6 functions of 3 variables. Now, the beautiful application, elegant application. Einstein pointed out that freely falling observers see flat space about them. Proceed on. Hence, the geodesics are straight lines in that frame. Solving the time-like geodesic equations in the given coordinates, we obtain the 3 vectors orthogonal to the line at each point. Proceed on. Putting them together, we get the flat space-like hypersurfaces by only solving the geodesic equation. So we also know the criterion for the existence of a flat foliation, that there exists a free fall frame, i.e. a non-accelerated frame, and obtain the flat foliation without solving those 6 nonlinear partial differential equations for 6 functions of 3 variables, and out comes the answer. Let's proceed on. The particle physicist who used group theory, Eugene Wigner, talked of the unreasonable effectiveness of mathematics in science. That's where the title came from. But is it unreasonable? Ask yourself. Or is this one more instance of extolling mathematics by specious argument? Please proceed. If you have a car and need to loosen or tighten the bolts in the engine, you will make a spanner that fits the bolts. Proceed. Is it unreasonable that the spanner fits right for the car? Well, obviously it will. But perhaps Wigner was remarking on it fitting all cars. However, when you manufacture cars, you want them to be easily maintainable by available tools. Then don't we make our theories such that our mathematical tools can be easily used on them? Yes, we do. Let's proceed on. The proof is that when problems arose that were beyond the existing mathematical tools, new ones were invented. A novel problem came to the attention of Pascal and Fermat. Gambling seemed to depend on luck. Pascal and Fermat tried to take the luck out and formulate a strategy to win more often than they would lose. This is what developed into probability theory. Let's proceed. There had been many problems of explaining the behavior of matter where Newton's laws did not seem to be usable. After the advent of probability theory, Maxwell was able to explain the behavior of gases seen by Boyle and Hooke, and by Charles and Boltzmann, and later Planck and Einstein could then use it to explain more of the behavior of matter and radiation. Let's proceed. Was the applicability of probability theory unreasonable? Let's proceed on. Gauss was tasked with conducting surveys on large areas of the Earth. He needed to use geometry, but Euclid's geometry was restricted to plane surfaces. Now, there was among the Greeks already spherical trigonometry, but it was not versatile enough for surveying on the Earth. He needed more general results. Since there were none, but differential calculus had been developed, he invented differential geometry. There had been many other attempts at developing non-Euclidean geometry that had not been fruitful. However, Riemann generalized it to higher dimensions, and then Einstein needed to use curved spaces for his extension of his restricted theory, special relativity, to arbitrary motion, and that's general relativity. After trying many others, found Riemann's worked well. See, what is unreasonable about the applicability of differential geometry? Of all the possible tools, he picked out that one. Now further, Adam Smith had developed economics as the study of competition for limited resources. All subsequent work in economics assumed the model of competition. But society had developed. And to get a society together, you require cooperation. The big economists like Keynes could not conceive how it would have evolved. I need you to go at my pace, not faster. Johann von Neumann and later John Nash developed game theory to explain how it could, how cooperation could arise. Yes. The whole point had been to explain how societies could evolve with competition and collaboration. Yes. It had been originally used for economics, but it was applied equally well for evolution of biological species and for societies of animals and humans. Let's proceed. Can that be called unreasonable? Yes. When nonlinearity became imperative to study complex systems, mathematical tools were developed for it. Yes. How unreasonable is it that the tools we make can be used for things we construct, or that the things we construct can be made with the tools we make? Yes. How unreasonable is it that the mathematics we construct is useful for our science, or that our science uses that mathematics? Is it unreasonable? Is it? I leave it to you. Yes, now maybe I should myself also look at all the points made.
Thank you, Professor Qadir. So that's the end of your slides,
here's
right?
a question. So I was just looking at the questions, and Manzoor Sabs I had answered that There was that one, but there's a whole lot more that there can be. The role of it in logics and decision making, etc. Yes, you need precision. If I talk about, let's hypothetically, somebody killing my mother, I will be emotionally involved. If I say, Mr. that the person X killed the person Y, that is the claim. Did the person X kill the person Y? I'm no longer that emotionally involved. Otherwise, at the beginning, I say, get the person so-and-so, because that's what's being said. That's the person. But I need to be objective about it and say, I don't know who did it. I know that this was done. Was it actually killed, or was it something else? Was it accident or what? Find that out. It will keep you out of the personal and into the precision there. Not only, there are many other logical errors that you get into. I can't really in this time talk about all of those. You can't have those things where it will come discussed easily. But a nice example, one example, is that the lawyer for the prosecution asks the witness, maybe the accused, have you stopped beating your wife? Answer yes or no. If he says yes, then he's admitting that he used to beat his wife. If he says no, he's admitting that he still beats his wife. You see, two questions have been rolled into one. One question, did you beat your wife ever? Do you now beat your wife? Two separate questions. Now, these type of things are discussed in logic, and I really can't at this time give more and more examples of these types. But it becomes important for decision making as well, because you see, I want to know, here's some risk, here's some profit, and is this worthwhile or not? Well, I need to keep the logic clear. Is the risk so much? Isn't all? Is it too much? Is it something I can't possibly allow for? Then that will be a cutoff there. I need to keep my logic straight. Oh, this is very, very unlikely, so that's it. Really, it's impossible virtually for your mother to survive. The probability is very low. Well, you're going to want to know, is it so low that I think it's no longer better to go on trying? That's a different question, and you'll confuse it. These type of things are what you need to use logic for. There's a whole lot more, but I won't try to go into all of those. So, yes, some set theorists like H. Woodin think that continuum hypothesis has a definite truth value, and they're trying to solve it by, I don't know how that will ever work, because Gödel's theorem I can state, and it doesn't really allow for much doubt. What he shows, and it is shown directly with the arithmetical language, I can construct statements with a given set of axioms. I can construct statements that do not fit in to that given set of axioms. Therefore, you have to bring them in as separate axioms. It was further proved that the axiom of choice falls within that once you have already accepted transfinite numbers and you're saying that then are they equal or not? So with the very question as asked, the proof is undoubtedly there. So whoever is trying to do anything about it seems to me not to be making much sense of it. It really requires more. You can go on with any set theory. We say essentially what they're doing is saying there is no continuum. Just that is my assumption. There is no continuum. And if there's no continuum, everything is fine. I don't have a problem. None of those people needed to die crazy. But I do have a problem. I can go on adding numbers and multiplying numbers. I can do the next steps as I can go on, and I do have to follow Cantor to say that that is possible. Unless you're going to rule something out by fiat, which is what is done there. When you rule it out by fiat, you aren't saying that now we've got that solved. You're saying, I refuse to look at it. Now that's all wrong. Just, I'm not going to believe it. It's all wrong. That's no answer for a mathematician. When people do it, they're hiding behind their jargon to try to do it. You have a very clear logical sequence of steps, which I showed, and there's no way out of them. That's why I was, Sumro Sahib, I was saying, let me first go with this. This one I can talk about and get right to the end of the point. And when I get to the end of the point, that is the end of the point. And when these people are trying to do other things, it is actually going with hidden one way or the other fiat. This is not possible. What they say in that is all of this talk of transfinite numbers is wrong by definition. Power set of a power set with the, or even the power set of the natural numbers and infinite set is got more element. No, all wrong. I define this consistently, and here it is consistently. What's wrong with what that was doing? Well, that's all wrong. When you go with that's all wrong, you can do anything. That's where you do need really logic rather than just that's all wrong. That's a common thing that people do. And there's a beautiful example I have, nothing to do with mathematics, but which I'd like to give. I was looking at a newspaper, and there was an article about nuclear weapons by one person, a supposed expert on defense, defense and strategic studies. There was on the opposite page a paper by an article by Parvez Hoodbhai talking about it in a totally different way. Not that they were opposed to each other. I asked that first person what his comment was about Parvez's article. He said, yes, but you see, he doesn't understand defense and strategic studies. He's not an expert in it. I said, yes, but then what is wrong with it? Well, he's not an expert in it. I said, but how is yours right and that wrong? He said, well, I'm an expert. I have a PhD in it. I'm an expert. This is arguing by fiat. It is true because I say it's true. My degree says that I'm the expert. The degrees don't say anything. Degrees tell me only that somebody has assessed your thesis and said you can go through on that, and whether they were right or wrong, good or bad, anything, I don't know. So this type of argument, when it is used in mathematics, is even worse. There, I'm ready to give that person the slight benefit that he forgive him for he doesn't know what he's saying. But here, the mathematician should very well know what he's saying. That is my answer there. If there are any other questions, I will
Thank you, Qadir.
try to answer. Oh,
Did you
yeah,
get a
there
chance? Did you get a chance to look at the question from Imtiaz from Qadir University?
yes,
They want to
there is a
ask.
question here. I'd like to just refer to this question. Imtiaz from QAU, I think, is the one asking. And
Yes.
being a senior mathematician, what's your opinion on the day-by-day decline of mathematics in Pakistan? Youngsters are not interested in learning mathematics. This is not just here. It is actually worldwide that all people are bemoaning this. They're bemoaning people, young students are not interested in physics even more than in mathematics, but the mathematicians only look at themselves, not at the others. They even more so with history. Nobody's interested in seeing history or philosophy. You just don't find any philosophers or practically anything. What is the real problem with the decline in education over the whole country? That is a question that should be discussed, pondered, and I have my opinion on it, that how we went wrong, when we went wrong, where we went wrong. There is the problem generally, and there's a particular problem of Pakistan. And I worked over 50 years to try to improve things. And in fact, we succeeded to some extent, and then everything collapsed. I have to say we failed, all said and done. And I can tell you what all went wrong. I'm not presenting that as an excuse. I'm giving it as a statement of what happened. And when you ask next, how can we fix it? My answer is, I don't know. If I had solutions, we wouldn't be in the mess we're in. I thought I had solutions. I tried. Things did improve, and then they collapsed. Now, what would be the solutions? And I say the young generation has to find the solutions. I can help by telling you what went wrong, how, when, where. How to fix, you have to find. You have to do. I'm at the end of my career. You people have to find a way out. Not only this, for the whole world, this is a problem, but that's not the biggest problem. Our climate destruction as it is going, we are extracting too much water from the natural aquifers over the whole world. Pakistan is doing less than most others because we can't manage. The amount of water being pumped out is now leading to the flooding and inundation. Wouldn't you like to tackle that rather than why do students not come into mathematics? Why do you go on consuming and consuming and consuming? I know why the producers go on producing and producing, because you consumers go on demanding and demanding, and then they go on producing and producing. Why not tackle that problem? Our problems at present are many and all pressing. Local Pakistani problems worse than others, but the global problems are in another way worse. They'll take us down and down to the whole world will be destroyed. It will be drowned. That's where we'll go. Sorry, that is my answer to what was it, imtiaz. What is the number? Why the number of women is increasing? The number of people is increasing, not the number of women. The number of people, men, women put together, number of children is increasing even more. There are reasons explicitly, there always were more females than males, and in many species that is a matter of course. In the human species, there was a slight difference, not very much, not all that much. There was much greater mortality for females because they would die during childbirth. So that was there. And here, it is dead easy to say attention to elementary education is the solution. How? How do you get elementary education done? Do you have any idea of how many people have to be taught? Out of 250 million, 120 to 125 million have to be taught. Take a 25-to-1 ratio for teaching. 5 million teachers required. Not 5 million teachers. 5 million competent teachers. Do you think you have 5 million competent teachers? You need to teach the teachers. So when you teach the teachers, let's say again that factor of 25, I need 20, that was 5 million and 25. So I need, is it 200,000? 200,000 teacher trainers. Can you manage that? Okay, we'll go one further step. Factor of 20, not 200,000, just 10,000. Even that you don't have. One more step. But if you're having teachers produce only teachers, produce only teachers, produce only teachers, you're going nowhere. It's a free wheel which doesn't drive an engine. That won't work. At least half must go back into society and do things for the economy. That's a factor of 16 for each step, factor of 2. And the total time taken, I can't help it, it's about 20 years. Do you have 20 years? In the meantime, your population goes on increasing because you won't cut it down. You won't stop, you'll go on producing. Oh, this maid who died, the mother had the problem. Oh, she hasn't as yet died. The mother had the problem. She has 10 children. What can she do? There's an element. How can she manage? And did I tell her to have the 10 children? When you can't manage to maintain them, you don't produce them. But, oh, that poor woman is what one talks about. No, it's not poor. That's another problem. So attention to elementary education is not the solution. There is no such single solution. You have a much more complicated problem, and any simplistic attempt, this is how we'll do it, won't work. Sorry. You have to go deeper. You have to find me answers how to do it, not with this trivial method. Try to see how you would actually get that done. I did try. I actually put in systems to try to improve. The political will isn't there. They didn't go on with it. Worked brilliantly, beautifully, and then it just left alone. The political will isn't there.
So, Professor Asghar, thank you so much.
Mathematical society, which mathematical society of Pakistan? Unfortunately, we have too many. There should be one body which represents all the mathematicians. I suggested to the Pakistani Academy of Sciences that it have such a society which will give policy decisions and so on for it. The Pakistan Academy of Sciences said, no, if we give it for the mathematicians, we'll have to give it for everybody. I said, sure, well, do so then. No, we can't manage to do that. Sorry, this can't be done. Well, I tried, but it just, that academy didn't give any support.
Please, Qadir.
So that, Manzoor Sahab and Imtiaz Sahab, is my answer. They're managing in Iran, and bear in mind there was a time when the Iranis used to get Pakistani teachers to go and teach mathematics there. When the South Koreans came, they came to learn from Pakistan how to develop economically. And much later, they came again to tell us how to develop economically. And one of the members, who was the team member at that time, had been a junior member, said, I don't understand how it is. We just took your plans, implemented them there, and everything has developed as you see it. We've gone places. Why is it that you haven't? Well, the answer is the political will isn't there, but our academics were not ready to actually push for that enough. That's the academics weren't ready to do it. We could have done something in there, we weren't wanting to try. Oh, sorry, that can't be done. We have to recognize the work of elementary teachers. That's one part of the solution, certainly. It's not the whole solution. It's just one part, very small part. You need to actually recognize the elementary teachers, the secondary teachers, the higher secondary teachers, the university teachers, all put together. You need to at each stage recognize and try to fix things there. I can give you the horror stories of what happened with education at the lower levels. Give recognition is far from it. Give them their ready salary, they don't do that even. The clerks would withhold it, would charge bribes to give a part of it. Give them recognition, actually do something with it, actually show how. How will you stop those ready clerks doing what they are doing? That's political. You have to fight that political battle. You people have to do that. I tried. We were doing it to some extent, but there just weren't enough of us to do things. The kids will learn mathematics if we make mathematics relevant and if we teach it properly. We don't. Let's face it, we don't. There's no life in the mathematics that is taught by practically anybody. That's what I was saying, competent teachers, not just teachers. ये याद कर लो, ये बस करो. तो सवाल पूछता है, बैठ जाओ, तुम तंग करते हो, तुम ये शरारत कर रहे हो या क्लास को खराब करो. अच्छा निकल जाओ क्लास से. Is that the way we're going to teach mathematics? Not that way, sorry. Ali Rajali, that is the problem. You have to actually get them the recognition. You have to actually get the salaries to them. You actually have to ensure the teachers teach with some life to them and actually try to motivate and take them forward. You aren't beginning to do that. Your teacher training doesn't begin to do that. It tells you that if you're in the classroom, here's the blackboard, there's the window, you should stand here and not there. That's all they teach. You have to find out what the problems are before you begin to give solutions. The simplistic answers are not adequate. You have to go deeper. You have to actually get your hands dirty by seeing what there is on the ground. When I tried to go with curriculum revision, I asked for a committee, and from Islamabad, the girls' colleges sent two representatives. I'd asked for equal number of boys in girls' colleges, and the boys' college was not represented. I insisted that we want those. And finally, one came, not two, and had no idea of the problems that they were facing for teaching. There were girls' colleges, people did. That's the problem with tuitions and tuition centers. And you have to actually get into the nitty-gritty details. You can't get answers, solutions from the air. Get down to the ground and see what is going wrong. I can tell you a lot of what is going wrong in a short talk. I can give you a whole detail. If you come to it for the longer thing, I can go on with the nitty-gritty detail. But don't tell me a simple answer. Give me something that will work. I tried not simple, I tried fairly complicated, and it didn't work because of the society not supporting it. The society as a whole, not the mathematical society as a whole did not support the changes. They weren't ready to do that, to get out of their little ruts and niches and start doing things. Is it the calculus, or do we need to improve a new system to calculate? I am sorry, Muskan Zara, I don't think that's a sound question. Which branch of mathematics contributes to space exploration? No, it's electronics. In one sense, it's a number of things, but you have to know what you want to do and then just see what is required there. You have to make those rockets. Who's going to pay for them? Is it the calculus or the method of calculation? Irrelevant. You have to see what you are going to try to do. How will you run it? How will you go on paying all the people who will have to be paid? Will you go and pay work for free? Have you seen how people in the old days when science was being developed in England, how much they were ever paid? Who paid them? You have to wake up and see the real world and try to do something with it. Not with these superficial attempts. That won't work. Go to the details. The devil is in the detail. You have to get to the detail. If you're finding answers, get to the detail. You actually have to find out all that went wrong. Anybody else?
Thank you, Professor Qadir. I think that's the end of the Q&A session.
Here, Iqra Akram said, I think we should reduce our curriculum, especially at elementary level. Much greater detail of what is suggested there is needed. Reduce our curriculum is too vague. I can reduce the curriculum by cutting out Alif, Be, Pe, and ABC, and 1, 2, 3, and just have other things. That will reduce the curriculum, and we'll go shooting up. Right, Iqra? You have to tell me, what are you wanting to reduce? Which thing, how, why, when, how much? Elementary is a wide range. How much will they learn by the end of it? What are the things they learn by the end of it? What will they not? I would stress, all of you people are not that young, that small, that you're not seeing where things could go. you have to get to those details. Don't try to go with simple things like, I think we should reduce our curriculum, especially at elementary level. I don't know what we're talking about there. If we reduce the curriculum not only then at elementary level, you're going to reduce it at the secondary level, then you're going to reduce it later. So you feel, therefore, that we are people at the universities are far too highly educated, they know too much. Would you really like to convince me about that?
Cool.
No. No. Yes. Yes. Well, arrange to meet me online or whatever. Arrange to meet me, and then I can discuss with you how that will do it, that we are too actually highly educated. I don't agree with you at all. We're not
I think that's wonderful of you. That's grateful. We enjoyed this talk, and the feedback that we have received from the audience is quite engaging. So thank you once again. And I would like to apologize all the participants that we got delayed a bit in the beginning because there were some connectivity and screen sharing issues. But nevertheless, it was a great talk by Professor Asghar Qadir, and we are extremely grateful to him. And I would like to remind that this talk was brought to you by the Economic Cooperation Organization, ECO Science Foundation, and the Union of Iranian Science and Union of Iranian Societies of Mathematical Science, UISMS, from Iran. And this is a lecture series, and every month we would like to host similar talks once in a month. And if you have any of your speaker, the recommendation for any of the speaker for the next sessions, we would be glad to have the recommendations. And another thing that if you would like to receive the video recording or the news report of this webinar, please keep visiting the ECO Science Foundation website. We posted there. I think that's the end of this session, though it got prolonged a bit. But once again, we are thankful to everyone, especially Professor Asghar Qadir, for making this webinar happen. So thank you once again. That's all. Have a good day.